Thank you all for coming to my talk. My name is Suha Hussein. I am from Ain Shams University in Egypt, and I'll be talking about a collaborative work with Stephen McCament from University of Minnesota in the USA. Our work is about improving program verification for Java programs using fuzzing. Really, the idea here, when we talk about formal verification, it's one of those techniques that tries to model the program as a finite state machine that allows us to then talk about or reason about some properties and prove them or disprove them. And during that process, we take the program and try to translate it into that representation, usually in a logical formula representation that we can then pass to the solvers, SMT or set solvers, which then can give us one of two outcomes: either that the property is valid on the program under test, in which case it's safe, or the property is invalid and therefore it's unsafe, and that program is unsafe. And then it would give us, when it's invalid, it would give us a counterexample. So for example, here you can see on the left, this is a program that tries to check a pattern within a string. Basically, it tries to see if that input string has the word fail on the even indices where it starts with the index 0. And on the right, you can see some translation of a particular control flow that can reach the assertion failure on line 8. And this sort of translation is what we pass into the SMT solvers that would then give us whether it's a safe or unsafe, and then if it's unsafe, it would give us this counterexample. The counterexample is really a very useful output because it can help in iterating on either the program or the property. So it helps us to understand where our expectation went wrong and whether we need to make changes to the program or to the property that we were trying to prove. However, these are not the only two outcomes that you can get from an SMT solver or any solver in general. In fact, you can just get a timeout or unknown, which, in which case you really don't know how there's any direction to go forward. Like, in what way can I improve the program or the property? And this is really essential because, when the property is valid, there's nothing really to be done. It's useful to know where things are going wrong, and it's crucial because that helps us iterate on the program. So anyways, we get sometimes timeouts or unknowns from the solver, which are not very useful. So here, for example, is one program that's actually used in SVComp, which is a popular software verification competition. This program is about adding two numbers, so pretty simple. It's adding M and N, and you can see here C, which is, so this addition is happening in a recursive, using recursive invocations, and C just describes the depth of that invocation, and there is a made-up assertion failure here at line 6 whenever that depth reaches 150. And when you look at the verification tools in SVComp 2025, you can see actually none of them were able to get to that assertion failure. So Java Ranger runs out of memory, JBMC and GDART, they time out in the 15-minute time budget. So that's another example here you can see, which is about, so you can see it's very simple in terms of doesn't have any branches or anything. It just relies on some heavy math functions, trigonometric functions, which none of the verification tools, again, is able to handle because they are difficult to translate to their corresponding representation in SMT or their logical representation. So on the other hand, when you look at fuzzing, fuzzing can be helpful in these situations. It really is about testing programs on some inputs that are likely to achieve new coverage. And it doesn't require any mechanism of translation or anything like that. It will just keep trying to get to deeper part of the code. So in that example I was talking about earlier, where we try to check a string for a pattern with the word fail, the fuzzer would just start by any random string, and then it tries to run this program, then collecting coverage as the program executes. And because the first string that is passed will achieve some coverage, it will then decide that this string is interesting and I should mutate it further. Perhaps it can help me get deeper in the code. And it can do that. It can provide then the 2 and 3 inputs, for example, here, where some mutation has occurred on the first input, but unfortunately no new coverage is achieved, so they are disregarded. However, at some point, maybe on the input number 4, there has the right mutation, especially for the first index to be the letter F, in which case it will then achieve a new coverage at line 4, and then that new input is then determined as is recognized as an interesting input that should be mutated later on. So the fuzzer can keep doing that, trying to mutate pieces and then determining interesting inputs and keep mutating them. At some point, it can reach that assertion failure at line 8. So in this work here, we argue that coverage-guided fuzzing can really complement the verification technique, and it can help us improve the reachability of the falsification, and thus it can help us provide this iteration to improve the program and our understanding of the property that we want to prove over our program. So to do that, we actually built on top of JQF AFL, which is an extension of the AFL fuzzer to Java programs. And we've added 2 main components, one that intercepts the creation of symbolic objects during the verification, and then the other is about enforcing assumption checks. So to intercept the creation of symbolic objects, basically the idea that is whenever we see that there is a symbolic object is about to be created, we ask AFL to give us the random stream of bytes that with which we can create the corresponding type of symbolic object. We actually support we support all Java primitive types, and we use this mechanism to create them. Along with that, we also provide a mechanism to create the Java string object. In fact, in the paper, we provide an algorithm that uses or parses the random stream of byte into a UTF-8 encoding so that we can increase the likelihood of generating useful strings. So the second component is about enforcing assumption checks, and in this step what we do is that in many cases in the program that we want to prove or disprove some property about it, we want to constrain to the input with some condition. And so to handle those conditions for the fuzzer, what we provide is that we use the generate and check approach. So basically we just generate an input and then we check if it passes the assumption check or the constraint that it should be imposed on the input. If not, then we disregard this input and then generate a new one. If yes, then all things is good and then we proceed. So basically it's just a simple generate and a check approach. So for the evaluation, we've actually added these extensions to JQF AFL, and we ran verification tasks from the popular software verification competition SVComp 2025. In total, there were 420 unsafe verification tasks that we done our experiment over, that existed in 2025 and which we run our experiment over. We run our version of JQF AFL. Again, it's the participating tools Java Ranger, JBMCG, and MLB. And we were interested in answering 3 questions. Can fuzzing solve verification tasks? What are the types of verification tasks that the fuzzer can actually have advantage in? And the third question is whether we see any performance that we, what's the performance of the fuzzer? So I'll be talking about the first 2 questions, and the third one is in the paper. So to answer the question about can the fuzzing actually solve verification tasks, you can actually see here JQF, AFL, against all the other tools. You can see that we were able to find 277 of unsafe verification tasks, which might fall into the lowest among all of the other tools, but yet not too far off. Like you can see also Java Ranger, which is the gold medal, gold medal winner of 2025. The closest actually to JQF AFL. But if you also look at the incorrect results, you can see JQF AFL by design cannot say any wrong results. Like it cannot say that it cannot find that the property is correct, and the reason is that it will just keep searching for one. It can never. It's an incomplete approach, so it can never claim that there is no violation. However, you do see complete tools here, like let's say the bounded complete tools, the Java Ranger, JBMC, and GDart. JBMC and GDart, there's nothing in them, like they are not saying the wrong thing. However, Java Ranger was saying the wrong thing in one of the verification tasks. This is probably just a bug, and Java Ranger just shows sometimes that there is a difficult machinery needed to do the appropriate translation to allow it to say the right thing. For MLB is really based on some search heuristic, that search heuristic over counterexamples, and sometimes that heuristic cannot find the counterexample, in which case it can say an unsound result. And here it happens to say an unsound result, incorrect and unsound verdict for 5 of the tasks. For the unknown task, again, you can see JKF AFL perhaps on the high end of having unknown. On the other hand, when you look at the unique tasks that were found by JQF AFL from each tool against each tool separately, you can actually see an advantage, like it's able to find 83 more unique tasks than Java Ranger and 54 than JBMC and so on and so forth. So it's able to find more tasks than each of the tools separately. In fact, when you look at all of them combined, like if you use all the verification tools in SVComp, still the JQF-AFL is able to achieve 3 more, it was able to get to the verdict of 3 unique tasks that were not found by all the tools combined. On the other hand, if you look at the converse, if all the tools can find verification tasks that JQF AFL was not able to get to, you can actually see 61 of those instances. And when we analyze them, we can see at least there's a potential of improving 14 of them, where JQF AFL just thought it found a bug when it did find something, but it was not the particular assertion failure. So there is an opportunity to improve on JQF AFL results here. If you look at the type of verification task that the fuzzing can have an advantage in fact, to answer this question, we looked into the different packages into the SVComp, and you can see here on a 6 out of the 10 packages, JQF AFL was able to get to 75 or more of the correct verdict about these categories. When you look at the where it had an advantage, it's clear on the float nonlinear package. You can see here it was able to get to 57 of them, as opposed to 5, 15, and 4 from JBMC and Java Ranger, JBMC, and GDart. And the reason for that is, again, these are complex floating functions that are these verification tools that completely translate to a solver formula or constraint had sometimes trouble in doing the right translation. And this is, of course, an advantage for JQF-AFL, where it can be useful at that point. In MLB, it's still a search. It uses a search criteria, so it still uses some heuristic. And in this here in this package, you can actually see that the MLB's search heuristic is better than JQF-AFL. If you look at the converse, where AFL was not doing great, you can see at the security bench package, which is more about finding a specific pattern in a string, which the verification tools are very good at, and they're easy to translate to a solver. But JQF-AFL was not able to find, at least in the 15-minute time budget. We believe that it can do better if we give it more time. So to conclude, we showed that verification can utilize fuzzing as part of its process, and we showed that there is an advantage of using the fuzzing to get into the falsification of properties easier, and therefore can help to improve and iterate on the falsification and improvements of the program and the properties. A promising direction, of course, would be to just try to utilize that within verification, the fuzzing within verification. Thank you all for listening, and I'm happy to take questions.